Okay, welcome to the next few videos, which will be on standing waves. This is by far one of my all-time favorite lessons or ideas to teach, because you can demonstrate this in a classroom fairly easily, and because the derivation of it takes into account a lot of kind of interesting, you have to do, it's a lot of steps to get to the answer, but the answer is so simple when you get to it that it's just very neat. I've always liked it. And it's not something that's super complex to understand. Once you see the derivation a couple times, you will understand it. To get there, though, we're going to split this into, I hope, 4 videos, and we're going to kind of slowly build our way up. So the first video, we're just going to be kind of laying the groundwork for what's going to come later. Standing waves are really important because they form the basis of a lot of phenomena. For instance, this is how musical instruments typically work, by having a standing wave set up in some sort of air column or on some sort of string. And what happens with standing waves is you get these interesting resonance effects that have a huge role to play in many, many different physics applications. So that's why it's also a very useful thing to know about. The definition of a standing wave. A standing wave is actually a superposition of waves. It's wave interference. It is 2 waves with the same, I don't know why I spelled that wrong, with the same wavelength and amplitude that are traveling in opposite directions. And what happens here is it results in a wave pattern that actually seems to stay in one place. Or in other words, the wave stands. Okay? Now I am going to show you again some simulations here, and the simulations should help you to understand how this works. So our first simulation, we're going to come over here and look at the screen. Now we have, I'll put this in the fast motion so that it's more obvious. We have a wave here, okay? It's a blue dotted line. Let me see if I can focus that a little better. Okay, there we go. We have a blue dotted line. And if I were to ask you what direction are the waves moving, like take a look at like that crest that just appeared. That crest is moving left to right across your screen, so it's moving towards the right. I would say that this wave is moving to the right. And obviously we know it's a wave because there's crests and troughs. If I turn off the blue wave and I put in the orange wave, we now have a wave. Watch the crests again. The crests move from right to left, so the crests are moving to the left for this particular wave. Notice it has the same amplitude right down here, and the frequency is the same, and the wave speed is the same, so that means the wavelength of each of these waves has to be the same. What I'm going to do now is I'm going to put both of them on here at the same time, and I'm going to slow it down a little bit. And I want you to notice a couple of points here that are kind of interesting. Notice at this point right in the middle, the waves are always have the same displacement, okay, from equilibrium right here. So right when they get here, their displacement is, not quite there. Right when they get about there, the waves are completely overlapped. Their displacement is as low as it's possibly going to go. Right about here, I tried to click it. Right about here, their displacements are still the same at this point, and it's as positive as it's going to be. And right about here, for this point right here, the displacements are the same, but the displacement is 0. There's a couple other interesting points. Take a look at this and this. These are exactly opposite, as are this and this, these points on the wave. And if we look at it in real time, they appear that they're always exactly opposite. So that's kind of interesting. And all these other points are kind of in between. Okay, so there's kind of 3 important points here. Here, here, and here. Now what we're going to do is we're going to, and I could put this back up to fast motion. what we're going to do is we're going to create, or we're going to click this button, and it's going to show us the superposition of these two waves. In other words, just these two waves added together. What would it look like? And it looks like this thick green line. Notice, I'll put it on real time, that the 2 points where it seems like the waves always have the opposite displacement, look at the green wave at that point. It doesn't seem to move. It never gets off of equilibrium. Okay, it's kind of in place. On the other hand, look at the point where we said that the waves always have the same displacement. That point is varying wildly back and forth. Okay. Also notice that the amplitude of both these waves is about 2 centimeters. The green wave, the superposed wave, that has an amplitude of 4 centimeters at its height, at its maximum. Okay, so this is called a standing wave. Notice that even though the blue wave seems to travel to the right, the orange wave seems to travel to the left, the green wave doesn't seem to be doing anything. It just kind of stays there. I can set up another standing wave if I change the frequency by keeping the wave speed the same, so I'm actually changing the wavelength as well. Let's see, I think it's right about here. This is another standing wave. If I take away the green wave for a second and I take away the orange wave, notice that I have a blue wave traveling to the right. I have an orange wave traveling to the left. And the combined wave doesn't seem to move to the right or to the left. This is also a standing wave. This is simply a different type or different mode of standing wave. We might say it's a different mode of oscillation. And as I adjust the frequency, given this particular length right here, as I adjust the frequency, I'll find more sets of standing waves. There's one right about here. One about there. And imagine if this was, if I could go into even faster motion, what this would look like to you is not necessarily that you can see the wave oscillating back and forth between its two states. What you would actually see would almost look like loops here. It would be moving too fast for your eyes to see. You would see a loop here, you would see a loop here, you would see a loop here as the wave, as the superposed wave goes from here up to here. You would see a number of loops, and you would also see some points where it seems that the wave kind of doesn't move anymore. And again, in class, I'll show you this again as well. So there's a whole number of standing waves that are happening, but the key here is that the standing waves happen because you have two waves with the same amplitude and the same frequency / wavelength that are moving in opposite directions. Okay, so we're going to write all that down. So here's our picture. Let's say we have, here's a graph, we have we have this wave moving to the right, and we add on to that this wave moving to the left. These waves are not very well drawn. What we end up with is a combined wave that is twice the height of both of these, and it oscillates between a few different positions. At some points we see the wave like this, but at other points we see the wave at the dotted line. And it oscillates between these two modes. Wave alternates. And again, the reason it alternates is because this is due to the interference, the superposition of these waves. The wave alternates between the full and the dotted lines. And we actually have names for the different parts of this standing wave, what it looks like to us. The points where the wave does not seem to move, where the string in this case doesn't seem to ever leave equilibrium. So for instance, right here, right here, right here, here, and here actually. These are known as nodes, whereas the loops Okay, the entire loop, not just like this one hump here, but like this space, this spot right here, this position on the x-axis, these are known as antinodes. I know I'm kind of squeezing that in, okay? It says antinodes. So we have nodes where the wave does not seem to move off of equilibrium. We have antinodes where we have a lot of movement off of equilibrium. And again, remember that the points where it doesn't move, that's because of destructive interference. The waves are destructively interfering at those points. Antinodes are places where there can be a maximum constructive interference. Okay? So, standing waves are fun to look at, but we want to talk about the applications. Before we can get to things like waves on a string and predicting what frequencies standing waves will be set up at, because it's not every frequency that gets a standing wave set up at it. Matter of fact, here I'll show you. If I just do kind of a random frequency, okay, so that has a standing wave set up in it. If I change this, oh, okay, I see why. A standing wave also by definition, so okay, never mind, this is a bad example. We're just going to go back. I forgot that simulation kind of makes it so it's a standing wave no matter what, even if you have one end that's kind of flapping wildly. If this was actually on a string, that particular frequency would not look like a standing wave. Okay, so anyways, before we can get to waves on a string and figuring out what frequencies will cause perfect standing waves that don't seem to move, we need to talk about how waves can get reflected. There's really two types of reflections here. We can have reflections at a fixed boundary, and we can have reflections at a movable boundary. And we will test both of these out in class. Okay? So a fixed boundary would look something like, let's see here. Actually, let's do a movable boundary first. Okay? So on a movable boundary, let's say that we had a picture of, okay, so let's say here's here's a wave, here's a pulse on that wave, and it's the string that the wave is traveling on is attached to a little like ring sort of thing, and that ring is on like a post. It's attached to like imagine one of the steel the metal bars that I have in class, and the pulse is traveling this way. Okay, so here's what I'm going to do. I want you to watch what happens when I create a pulse. This is a different simulation. Watch what happens when I create a pulse and it moves towards this movable boundary. Okay, so there's our pulse. Hits the boundary, and look at that. It gets reflected back the same way. Let's look at that one more time. There's the pulse. We can even look at it in slow motion if you want, step by step. Hits the boundary. The ring slides up, and the wave apparently is reflected back the way it came with the same orientation. Okay, so if we're drawing pictures of this, here's what it looks like. We transition down to our next drawing. We have the ring really high up here, and then as the ring slides back down, pushes the pulse back the other way. Okay, so what is happening here is the string pulls on, we're going to say the boundary. In this case, it's a movable boundary, that little ring. And it moves it up, or moves it in direction of pulse displacement. So, moves the ring in the direction of the pulse displacement. This pulse displacement is positive, so it makes the ring move in the positive direction. But then, once the ring is up here, now the string is pulling back down on the ring. So that ring's going to fall back down, and it basically recreates the pulse and sends it back the other way. So string then pulls in opposite direction on the boundary. recreating, that says recreating the original pulse but traveling in the opposite direction. Okay? That's what happens when a wave hits a movable boundary. The wave gets reflected back with the same orientation. Now let's take a look at what happens if we have a wave that hits a fixed boundary. So this is a fixed boundary here, as long as I'm not pulsing. So we're going to hit play, and we're going to watch what happens. Okay, so it's approaching it, and something different happened. It seems to have inverted this time. Let's look at it one more time. So, okay, so we have that. Okay, so the wave is coming back, and watch again, and we can watch it in slow motion if you want. We actually have destructive interference for a second, and then the wave seems to invert. And then it continues. When it hits the movable boundary here, it's going to stay the same orientation. When it hits the fixed boundary here, it's going to flip. So you can actually predict kind of what's going to happen. Flip, stay the same, flip, stay the same, and so on and so forth. Okay? So, what's happening here at this fixed boundary? Okay, here's a wall. We have a pulse, or we have our string, and we have a pulse going this way. So what's going to happen here, it's very similar to the movable boundary, but obviously this string is fixed to the wall. It's not going to jerk the wall up with the string. The string pulls up on the boundary, but doesn't move it. Because of Newton's third law, if the string pulls up on the boundary, then the boundary, in this case the wall, must be pulling down on the string. And what this does is it inverts the string. The string gets accelerated downwards, and it ends up sending the pulse back inverted. So, here's our wall. Our pulse has been inverted, and it travels back the other way. Before I go, I want to point out, what does the boundary represent in both these cases? If we have a spot where the displacement of the string does not seem to change, or doesn't change from its normal position, even with the string pulling on it, what did we call it up here when we had a spot on the string where the displacement didn't change? We called it a node. So here we would say that where the wall and the string meet, that is the location of a node. On the other hand, when we had the movable boundary, that ring would go up, that ring would go all the way up, and it could move. It would go all the way up if this was a positively oriented pulse. It could actually move. What did we call the points on the standing wave where the wave would undergo constructive interference, where the wave seemed to move the most? We called those antinodes. So for a fixed boundaries act as nodes. Movable boundaries act as antinodes. So we have antinodes, or not plural, just antinode, where string meets that movable ring. Again, we'll see this in class. I'll demonstrate this for you guys a couple of times. And this stuff is mostly prep work for what we're about to do when we talk about how waves on strings interact if we want to set up standing waves. I'll be back for that video in just a little bit.